We are going to discuss a few problems on generating functions. Now, generating functions mean mainly we concentrate on the probability generating function of a mainly discrete random variable, and we consider the random variable to be non-negative. Now, we know the definition of probability generating function, but it is interesting to see that we can define generating functions from some other events, like or we calculate or we try to evaluate the probability of some event with respect to the original random variable, say x, for which we have defined or we have derived the probability generating function, say ps. And with respect to x, we can define some event and we can calculate the probability, or we can have some other expressions. And for those expressions, we can evaluate the probability generating functions. So this technique is very easy, very simple, but it requires some algebraic manipulations, very simple algebraic manipulation, maybe in some cases school level algebra. But it is interesting to see that the generating function can be written in terms of the generating functions of the original random variable. Okay, so we will discuss a few problems, mainly one problem, and after that we will try to exploit the relationship between characteristic function and the distribution function, and we discuss few interesting problems. A few interesting problems in the sense that, as for example, we know that something has happened when we are dealing with some normal random variables, but the question is whether the converse is true or not. I am not going to tell you which property I am going to discuss, that will be revealed eventually, but it will be very interesting, and all these problems can be dealt with or can be solved using the characteristic functions, because we know that there is a one-to-one correspondence between characteristic function and the distribution function. Now, today we are going to discuss few problems on some generating functions. The first one is based on probability generating function. The problem is from the book by A.K. Basu. Let PS be the probability generating function, that is PGF, of a non-negative discrete random variable. All we have to do is to find the PGF of probability capital X greater than equals to n. That means this probability must be a function of n, and we have to derive the probability generating function of that function. So we start with the we know that the PGF of x is defined as, let's check the definition of probability generating function of a random variable. Of course, we assume that the random variable is non-negative. So P of s equals to summation k equals to 0 to infinity pk into s to the power k, which means actually expectation of s to the power k, where pk is nothing but probability capital X equals to k equals to 0, 1 and so on. So this is the way we define probability generating function of x. Now we have to define, or we have to derive, the probability generating function of the expression for the probability capital X greater than equals to n. Let's call it Qn, because as I mentioned that this must be a function of n. So now how to define the generating function corresponding to Qn? First, note what is the meaning of Qn in terms of the simple probabilities based on x. So Qn is probability x greater than or equals to n, means probability x equals to n plus probability x equals to n plus 1 plus probability x equals to n plus 2 plus and so on. That means in terms of the notation, we can write immediately that this is equals to p suffix n plus p n plus 1 plus p n plus 2 and so on, which is summation r equals to 0 to infinity p of p suffix n plus r. So this is nothing but Qn, but we have to derive the probability generating function for Qn. Let Qs, capital Qs, be the generating function of small qn. Then naturally we can immediately write, looking at the generating function of Px, we can immediately write Qs equals to s to the power 0 into q0 plus s to the power 1 q1 plus s square q2 plus and so on. Now remember, Qn is summation r equals to 0 to infinity p of n plus r. So just replace this quantity in terms of p's. That is, first quantity q0 is nothing but p0 plus, so if we put n equals to 0, this means q0, and summation r equals to 0 to infinity p of 0 plus r. So it becomes p0 plus p1 plus p2 plus p3 and so on, plus s into q1. Now q1 becomes, it starts from p1, so p1 plus p2 plus p3 and so on, plus s square q2 starts q2, the starting first term of q2 is p2, then p2 plus p3 plus p4 and so on. Similarly, s cube into p3 plus p4 and so on. Now all we have to do, so this is nothing but the generating function of qs. So basically we are done. But all we have to do is to write this entire expression in a relatively more compact form. It is very clear that you see, each in most of the terms, in many terms, few terms are common. So if we just separate the terms in from with respect to p0 or p1 or p2, we can immediately see that we can write p0 occurs only once, so p0, plus p1 occurs in the first term and in the second term. So we take p1 common, so p1 is into 1 plus s, plus similarly p2 into 1 plus s square, plus p3 into 1 plus s square, plus s cube, plus and so on. Now we know from elementary algebra that 1 plus s is nothing but 1 minus s square by 1 minus s. Similarly, 1 plus s square is nothing but 1 minus s cube by 1 minus s, and so on. Now little bit of manipulation. So this is simple algebra. As for example, we can take this, we can split these terms and we can take 1 minus s common, so that we will have 1 by 1 minus s into p1 plus p2 plus p3 and so on, minus 1 minus s into p1 s square plus p2 s cube plus p3 s to the power 4 and so on. So just simplify this entire thing, which I am not going to do right now, but simple algebraic manipulation will give us the expression, this expression, 1 minus s into ps would be divided by 1 minus s, and remember the range of s or s is defined only for modulus of s less than 1. So this is a simple algebraic manipulation in order to find out the probability generating function for probability, or for the expression probability capital X greater than or equals to n. So if we just change these expressions, or we can exactly similarly we can derive, or we can find out probability generating functions for other expressions in terms of ps, that is the original PGF for x. Next problem is another very interesting problem. We know that the convergence in distribution function, we have some idea about that. We know many theorems relating to this issue. So let us discuss one very interesting problem due to again Basu. So let fnx, that means a sequence of distribution function, let us define it as 0 if x less than minus n plus x by 2n if n minus n less than equals to x less than n, and 1 if x greater than equals to n. Show that fnx converges to fx. So, but capital Fx, where fnx converges, is not a distribution function, although fnx is a distribution function for every n. This is very surprising, very strange result, that a sequence of distribution functions converges, it is converging properly to another function. Unfortunately, that function is not a distribution function. Let's see how the proof goes. So this is the form of fnx, and it is clear that fnx is a sequence of a rectangular or uniform distributions. It is very clear. Now it is clear that fnx goes to half. If n goes to infinity, fnx goes to half, which is equals to capital Fx for all x belongs to R. But now this is true for all x, but capital F of minus infinity is not equals to 0, neither capital F of infinity equals to 1. That means neither capital F minus infinity is 0 nor capital F of infinity is 1. That means it violates two very important, or two of the four necessary conditions for a distribution function. So we can immediately say that capital F is not a distribution function. The proof is very, very simple. Now, if we recall our knowledge or our theorems or results or the idea about the characteristic functions, we can have some feeling that there is some kind of relationship between a characteristic function and a distribution function, or rather even there is a relationship between a sequence of distribution function with sequence of characteristic functions, and one can get the idea of convergence with respect to either distribution function or the characteristic function, and one can go from one end to the other. So the question is it possible to explore this problem in the light of characteristic function? Let's see. So suppose fnt is the characteristic function of capital Fn, then it is easy to show that characteristic function of Fn phi nt is sine of nt by nt, which again goes to phi t. Now phi t is interestingly 0 if t not equals to 0 and 1 if t not equals to, if t equals to 0 as n goes to infinity. Well, it is very clear that sine nt by nt, this limit goes to 1 if t equals to 0, and as n goes to infinity, numerator is always bounded by minus 1 and 1, so the denominator becomes very large for t not equals to 0, so it is nothing but the 0 value. It is clear that phi t is not continuous at t equals to 0. So a sequence of characteristic function converges to another function which is unfortunately again is not at all continuous at a particular point, in fact in this case at t equals to 0. And we know that phi t characteristic function is always uniformly continuous at t equals to 0, and so continuous at t equals to 0, so phi t is not a characteristic function. So since the sequence of characteristic function converges to a function which is not a characteristic function, by continuity theorem of characteristic function we can say that the sequence of distribution functions for which phi n is the corresponding sequence of characteristic functions converges to a function which is not a distribution function, or in other words, phi t is not a characteristic function, so we cannot find a distribution for which we can have phi t as a characteristic function, because it is in fact not a characteristic function. So this proof is very beautiful if we look at the proof from the characteristic function point of view. Now another very interesting problem that we have already used many times, that we know that if x and y are both normal 0 1, that means both distributed standard normal distribution, both are standard normal distribution, and independently, that means x and y are identically and independently distributed as n01 distribution, then we know that x plus y and x minus y are independently distributed. Of course they both have normal distribution, but the most important fact is that x plus y and x minus y are independent. Now one can ask that whether the converse is true. That means if we say that, so let us pose this idea as a problem. Let x and y be independently and identically distributed random variables with mean 0 and variance 1. If x plus y and x minus y are independent, then x and y both have normal 0 1 distribution. So we are going to prove this. This is a very interesting problem. So the solution should follow the path of characteristic function. So let phi t be the characteristic function of x and y. Since x and y have identical distribution, so we can say that phi t is the characteristic function of x as well as y. So the characteristic function of x plus y, it is clear that it is phi t square, and characteristic function of x minus t is nothing but phi t into phi of minus t. Simple algebraic manipulation can give you. Now we have one result. We know that kth order differentiation of phi t, that is phi upper bracket k of t, is minus infinity to infinity ix whole to the power k e to the power itx d of fx. And from here we have phi 0 as 0 and phi double prime 0 as 1. It's very interesting to see. So now, phi double prime 0 is minus 1. Now note that x plus y and x minus y are independent. Now we are going to use the fact of the given condition that x plus y and x minus y are independent. So let us start with phi of 2t. Now what is the meaning of phi of 2t? Phi of 2t is expectation of e to the power I 2t x, or we can write t into 2x. Now 2x I can immediately write as x plus y plus x minus y. Y and y cancels out. So let's keep this way. Now what advantage of writing this way, that we can immediately use the fact that x plus y and x minus y are independent. So we can immediately write this quantity as expectation of e to the power it into x plus y into expectation of e to the power it x minus y. Now as we know that characteristic function of x plus y is phi t square and characteristic function of x minus y is phi t into phi of minus t. So this gives us phi 2t equals to phi t whole cube into phi of minus t. Let's call this equation 1. Now put for every t alpha t as phi t by phi of minus t. This is a one small trick that we have to use. So this is one particular thing that we have to substitute. Then immediately we can write alpha 2t as phi 2t by phi of minus 2t. Just replace t by minus 2t. Now we know that phi of 2t is phi t whole cube into phi of minus t. Similarly, just replace t by minus t, we can get the denominator as phi of minus t whole cube into phi t. Now simple cancellation will give us, because one phi t cancels out and one phi minus t cancels out. So we are left with phi t whole square by phi of minus t whole square, which is nothing but phi t by phi of minus t, the whole thing square, that means alpha t square. So we eventually get alpha 2t equals to alpha t whole square. Let's call this equation 2. So it is interesting to see that in equation 1 we get the expression of phi of 2t in terms of phi t and phi minus t, and in equation 2 we can write alpha 2t, where alpha t is phi t by phi minus t, in terms of alpha t only. Now recall the theorem that if a capital F has absolute moment of order k, of course k is an integer greater than or equals to 1, then in the neighborhood of t equals to 0, phi t can be written as summation j equals to 0 to k I to the power j by j factorial m upper bracket j t to the power j plus some terms which can be neglected, where m upper bracket j is the moment of order j. So now we will use this theorem here. Now if we repeat the previous procedure as in 2 and also in 1, we can get alpha of t as alpha t by 2 to the power n whole to the power 2n. And we can immediately see that if we just expand it, we will get it 1 plus small o of t by 2 to the power n whole to the power 2n. Clearly this goes to 1 as n goes to infinity. Thus alpha t equals to 1. Since alpha t equals to 1, that means, or rather alpha t is equivalent to 1, that means alpha t actually goes to 1 as n goes to infinity. Alpha t is very close to 1, so we can immediately say that phi t is equivalent to, or more or less very close to, phi of minus t, which immediately implies from 1 alpha of 2t is alpha t whole to the power 4. And now repeating again the same argument and using the equation 3, we can write phi t as phi of t by 2 to the power n whole to the power 4n. And if we expand this, we can get 1 minus half t by 2 to the power n whole square plus some terms which are negligible compared to t by 2 to the power n, it's a function of this quantity, whole to the power 4n. And this is nothing but, if you just take the limit, we know that this is nothing but e to the power minus t square by 2. So we have to use some calculus, some limits here, which is very easy to see. So eventually we get phi t converges to e to the power minus t square by 2 as n goes to infinity. Now e to the power minus t square by 2 is a characteristic function of a standard normal variable. There is normal distribution with mean 0 and variance 1. So the proof is complete. Now remember, what is phi t? Phi t is the characteristic function of x as well as y. So we can immediately conclude that the distribution of x as well as y is nothing but standard normal 0, 1. I will conclude this session only by mentioning one small problem, that is, say let x and y be independent random variables having standard Cauchy density. We would like to find out the density of x plus y and x plus y by 2. Now if we can find out the distribution of x plus y by 2, is it possible to find out the probability density of x1 plus x2 plus xn by n if each xi follows IID Cauchy? Let's see. So let's start with the characteristic function. Note that the density of the standard Cauchy distribution is small fx equals to 1 by pi into 1 by 1 plus x square, where x lies between minus infinity and infinity. And the characteristic function of the standard Cauchy distribution is phi t, which is nothing but e to the power minus mod t. As you recall that this characteristic function is nothing but the density of the double exponential Laplace distribution except the normalizing factor, and the characteristic function of Laplace distribution is nothing but 1 by 1 plus t square, that is has the exact form of density of Cauchy distribution without the normalizing factor. So it is very interesting to note that there is kind of correspondence between the density function and the characteristic functions between Cauchy distribution and Laplace distribution. So first try to find out the characteristic function of x plus y. It is very simple. Phi of x plus y t equals to expectation of e to the power I t into x plus y equals to expectation of e to the power I t x into e to the power I t y, because x and y are independent, which means it simplifies to e to the power minus 2 mod t. Now this is nothing but the characteristic function of a Cauchy distribution, but not really a standard Cauchy. It's kind of 2 by pi 1 plus 4 plus x square. So this is again a Cauchy distribution, although not standard, but or rather the characteristic function. So by uniqueness theorem I can immediately say that x plus y follows a Cauchy distribution. Proceeding exactly similarly, we can derive the characteristic function of z equals to x plus y by 2 as phi of zt equals to expectation of e to the power I t x plus y by 2 equals to e to the power mod of t by 2 into e to the power minus mod of t by 2, because replace t by 2 and using the fact that x and y are independently distributed, again simplifies to e to the power minus mod t, now which is nothing but the characteristic function of a standard Cauchy distribution. Again by uniqueness theorem of characteristic function we can immediately conclude that x plus y by 2 follows a standard Cauchy distribution. Now this naturally motivates us to explore what happens when there are n identical, independently and identically distributed standard Cauchy variables like x1, x2 and so on to xn. What would be the distribution of x1 plus x2 plus xn by n? Now remember, this is nothing but the sample mean, but note that the population mean, the moments of Cauchy does not exist. So characteristic function of x bar is capital phi x bar t equals to expectation of e to the power I t into x1 plus x2 plus xn by n. Again, due to the independence of x1, x2, xn, we can write product k equals to 1 to n expectation of e to the power I t xk by n. Now replacing, now each xk follows standard Cauchy, so replacing t by n, we get the characteristic function of a standard Cauchy, which is e to the power minus mod of t by n. Now product k equals to 1 to n, which simplifies to e to the power minus mod t. So it is straight away clear that characteristic function of x bar is nothing but the characteristic function of a standard Cauchy distribution. Hence by the uniqueness theorem of characteristic function we can immediately say that the distribution of x bar has a Cauchy distribution, or rather a standard Cauchy distribution. So we have seen some very interesting problem. It is clear that the generating function q in this case of event in terms of x, that is probability x greater than or equals to n, can be written in terms of the probability generating function of x. There are many problems we can create in the same line, and it would be of utmost interest to study such problems. On the other hand, we have seen some very interesting problems using characteristic functions, and one of the very interesting problems, especially interesting to me, is that when x and y are IID normal 0, 1 variables, we know that x plus y and x minus y are independently distributed. But we had no idea till now that whether the converse is true. But in fact, the converse is true, which gives us some kind of characterization of normal distribution. And this proof is also sometimes a little tricky, but it's a very elegant proof, and we have seen that we can prove this result using a characteristic function. Another interesting thing is that we know that for a Cauchy random variable, expectation does not exist. Now, expectation means the population mean in common jargon. But we can define always a sample mean, because we can always draw some random samples from Cauchy and we can define the sample mean. There is no problem in defining the sample mean. The question is, can we find some distribution of the sample mean for a Cauchy random variable in a compact form? It's very, very interesting to note and to see that this sample mean again itself a Cauchy random variable. But remember, it's a standard Cauchy, and this distribution is independent of n. So the sample mean, which depends on the number of observations or number of variables involved in it, has a distribution which has no n, nowhere mentioned in the PDF of the distribution, because it's a standard Cauchy distribution. So that somehow indicates that we are not really going to get any information about the population mean based on the sample mean. In fact, that is true, because population mean doesn't exist. So we can interpret this result in many ways, but the proof needs some mathematical rigor, and that is through characteristic function.